So let's start. My name is Kate. I'm going to talk about how we use specialization to enable relational programming, or at least make it a little bit more feasible. But before going into that, let's start by thinking about why and how do we program. So usually we write programs not just for fun, but to solve some problem. So usually we have some problem in mind. For example, we want to find all vertices in a graph, which we can reach by paths from some specific one. And of course, we know with the algorithm for that, we just run a DFS or BFS or whatever we want. We write some code which does that. And already here we see that we need to do a lot of thinking about the details that don't really have anything to do with the problem itself. So we push something on the stack. Where the stack is in this graph? It doesn't exist in this graph, right? And we still have to think about it because it's the only algorithm that we can think of. And by running this program, of course, we solve our problem, but it's still a little icky. And then we come up with a new problem. So now we want to find a path in our graph from one particular vertex to another. And of course, we know the solution for that. We just modify DFS a little bit. We also store the path in the stack to that particular program, to that particular vertex. And we need to fiddle with that a little bit. And of course, by doing this, we can find our path and be very happy about that. But we will only be happy until we understand that there are more paths in the graph, which we can be probably interested in. And in that case, we need to find all of the graphs and we need to modify our algorithm even more. And it's all just highlights how programming is separated from our thinking about the problems itself. What would be much nicer is if we could employ our understanding of the problem, explain our understanding of the problem to the computer, and then just ask it to do the thing. And this is one of the dreams that people have been having for at least 100 years. And we still are not very close to that issue. So what is the core of our problem of finding paths in graphs? Of course, the cornerstone here is that we just need to understand what a path is. And here is the mathematical definition of it, which I think that everyone can understand without any issues and understand what's happening here. So a path in a graph is basically an edge and then a path. And they should be linked by one vertex. And this is exactly what our mathematical definition explains here. And it would be so nice if we could just shove it into the computer and let it do the thing. And fortunately, people created Prolog in the 60s or 70s of the previous century, which resembles our mathematical definitions so closely. So basically, we just say that there are two ways to form a path. In the first case, if a path is in between two of the similar vertices, then the path contains only one vertex, right? And if we need to find a path between two different vertices, well, in that case, find an edge, find a path. And here is just the complete definition in Prolog. And what is nice about it is having that, we can just run some queries to get the answers to all the problems we've had. So we can ask the Prolog program, is it true that there is a path from vertex A to F? And let it do a thing. And it will say us that there is this path. We can ask if there is a path between A and H, and it will refute it. It will say that there is no such path. We can also ask to find all of the paths between the two vertices. And here we use the variable P to store all of the possible paths in the graph. And what's nice about it is that it's by design non-deterministic. So if there are several paths, it will be able to find it. If you only want one path, we just ask Prolog to find one of them. And it's not always the case that Prolog can find all of the answers, but sometimes it does. So here, in this particular example, it says that there are only two paths between these particular vertices, and there is nothing more. And this particular logic programming thing is a very attractive technique, which we all would be, I think that we will all be happy to have. I think everyone can agree that we can just not think about the minutiae of programming, instead just formulate our problems in mathematical terms and then get our results. And of course, now we usually think about just formulating it in like a natural language problem to like shoving it into LLMs. So these are the LLMs of 50 years ago. And the issue with the Prolog, oh no, sorry, there is still one thing which I want to focus on, is that we can also solve problems like this, where we only are interested in paths between two vertices. And we don't really need to know anything about the path itself. So this is just a reachability issue. We can use this ignoring idea to ignore paths that are, ignore things that are not essential to the problem we are trying to solve. So all of this is like the power of Prolog programming, of logic programming, is that we list some facts that we know to be true, then we list some formulas between the facts, we run some relations, and then we get the results we want. Prolog has several shortcomings, I would say. One of them is that it is a separate language. It's kind of hard to work with Prolog if your main language is Java. It's hard to intro between them. And there is also some issues which come from the way Prolog programs has to be written in order that for them to finish working. So some people designed miniKanren. So Dan Friedman, Wilbert, Oleg Kiselov, they all came up with this idea of making logic programming a small DSL that you can just embed in any of your favorite programming languages and just do the thing. Just bring the power of declarative programming to whatever language you work in. So they created the Kanren family. These hieroglyphs are Japanese for Kanren, which is relation. And miniKanren is a small sublanguage of that allows us to create logic programming in any language possible. And here I provide two examples of prominent miniKanren implementations. One of them is in Racket, which is a dialect of Scheme, and the other is in OCaml. They look a little bit differently compared to Prolog, of course, but you can see the similarities. So you have disjunction of two conjunctions here. The first one describes the situation where we have a path between equal vertices, and the other is find an edge, find the path, and generate the result from that. So miniKanren is very nice, small, and easy to use language, which we tried to apply to our issues. And let me just spend just a little bit more on how it works, just so that we are all on the same page. I'll start with the syntax. So in miniKanren, you can create what's called relations. They are just programs in the language. They're usually written with this superscript O for some reasons. And you can call the relations that you created. You only have 4 constructions that you use to create your programs. So the first one and the most important is terminal unification. It's like the equality that we can use here. We have conjunctions, we have disjunctions. We also have this variable introduction fresh thing that is just a way to bring some variables into scope. It is a technicality right here. When it comes to how it works, the most important thing is unification. Unification may be familiar to you. If you have some terms in some language, you can check if they can be what is called unified, meaning that we can assign some values to variables in the terms so that they are the same. So if you have these two calls to f function here with 4 different arguments, we can unify them one by one and decide that if we have x to be equal to h a y and z to be equal to b, then these two terms are equal. And this is the thing that brings us to the ability of checking that. Let me just rewind here. It allows us to check that these two vertices are the same. So whatever edge we found, we can start path searching from the same edge, from the same vertex here. We need to unify these parts of terms in order to realize how they work. Of course, some terms are not unifiable. There is no substitution that you can create to make the two terms on the bottom to be equal. So you cannot make x to be equal to h and to g. There is no way to do that. And after we realize how unification works, then we just need to combine them in order to create the sets of answers that will be the results of querying our relations. So it's done with this stream operation, which is just a set of substitutions. We can merge them together. We can just make a union of them, append them, which is done with this operator. And we can also do the binding, which means that we first found the answers for some subproblem, and then we try to find new answers for the different one. And the conjunctions, disjunctions are this binding and plus consequently. And this is like the whole implementation of miniKanren. If you need the miniKanren in your language, you just write this, and then you can do Prolog. You think so, but it's not that easy, as I would describe further. One of the striking applications of miniKanren is creating solvers from verifiers. I mean by that the following. So there are basically two kinds of problems. One of them is just to check if some solution is a solution to our problem. So we have a candidate, ABD, and we ask, is this a path? It is really easy to write an implementation that checks that, right? We just check that there is an edge in the graph like that, that starts with the first two vertices in our list. And then we check that the rest is also a path. And this implementation follows from the definition of edge. You can write it in your favorite language easily. But once you try to solve a solution, to find a solution, find paths between some vertices, then you need to think about all of the issues and minutiae and stuff like that, the stacks and stuff. But in Prolog or miniKanren, you can create solvers from verifiers by writing them in the direction that you want. So funny enough, you can generate miniKanren program from a functional program easily by using what's called relational conversion. It's just a syntactic transformation. And then having this miniKanren, we can then run it in the direction which we want and get either verifier or solver. So if we fix a particular path, then we got to get the verifier, but if we just fix the vertices, then we get the solver that finds the paths for us. You can only write one program and get the solutions for everyone, for every single problem you have. Beyond the paths, we can see, for example, we can write an interpreter in your favorite language, and then you can run it forwards to get an evaluator, the interpreter, or you can run it backwards to get a program generator, for example. You can write a type check function and then get type inference and type inhabitants for free, right? It sounds all good and fun until you face the issue. And the issue is that it is slow. It is so slow that it's impossible to use for anything of worth. There are, of course, several sources of this inefficiency. For example, unifications are expensive. Unfortunately, this for operation of any logical programming language cannot be destroyed by its own in a logical programming language. The other thing which is common in miniKanren is that you need to take specific care to put conjunctions in the order that is good for your program, which defeats the purpose of the declarative programming, right? Because now you need to think about how it's going to be executed. You need to think about the details. This is something that we want to avoid at all costs. But we know something that can help us. And that something is the direction we are supposed to run our program. When we know something about arguments, we can improve the program to that arguments. We can specialize it to make a special program that works better. So this is where specialization comes into play. Just in case somebody doesn't know about this, the idea of specialization, if we know that a program is going to be always executed with some specific argument, we can translate the program into a different one, which is hopefully efficient. So for example, if I have a power program, power function here, we can, but we only need to always count power 5. We can specialize this program and create a program that doesn't do any conditional checking. It doesn't call power recursively. It doesn't do anything. We can just create a function which does the power 5 by multiplying. And this is the technical. This is the example of a more general approach, which is called specialization, where you can always separate your arguments into to be static and dynamic, analyze your program, create a program that already substituted everything that it knows about the arguments into it to get a program that works the same, but faster. And of course, specialization is something that has been done for logical programming languages, for Prolog. And we spent some time working it into a miniKanren. Let me show you an example. So here I have a fragment of an evaluator for logical programming, for logic formulas. Here we only consider a formula which can be a negation of another formula. If a formula is a negation of another formula, then we know that we need to evaluate it and then run a negation to the result. When we know the argument, the result of our evaluator to be true, for example, if we want to consider all of the formulas that can evaluate to true, then we can use that information to improve the program. So if you know that eval is going to be run with true for R, we know that it's going to be true for not here, which means that a variable is going to be false. It means that we're gonna call this eval with false, and we can improve that further and further and further. We can use this static information about arguments to specialize the programs to make them a little bit easier. And of course, in the end, we will just get something like this. So we will get two specialized function, one for evaluation to true and one for evaluation to false. They will hopefully be better. At least they don't call not here, right? And after that, we can get our improvement of time, of execution time. Let's see how it works from the bird's eye view. It's usually done by 3 steps. The first one is called driving. This is a symbolic evaluation of a program. We just try to replace all of the calls with the bodies. We can consider different disjunctions here separately. We can consider each of the calls separately and get a what is called a tree, which is then be used to create a new program. Of course, by doing this tree, we can run the problem that the tree grows infinitely, and we need to stop at some point, which is called folding. We usually fold when we encounter some calls that are either the same or similar to the ones we had before. Once we've done that, we can residualize it into a program that is hopefully a little bit better. So here we got rid of ender because we know that if we try to run evaluator with the results to be true, then end must have A and B to be true, and then we can use that information to propagate it and throughout the program. I will not go through the whole of the details of how it works, but we created a what's called a conspd conservative partial deduction method that allows us to treat miniKanren programs easily based on another method which was developed for Prolog before, called conjunctive partial deduction. It's finicky with the idea is that we don't always know which of the calls to consider. For example, here when we consider the disjunction of 2 formulas, we have 3 calls in the conjunction, and we don't know which of them should we drive forward to get the most information. So there is a little bit of a decision here that we have to consider to get the best possible results. One thing that we had to deal with is that in miniKanren, we can generate all of the answers always. This is the property of the search embedded into it. But unfortunately, it's very finicky with the conjunctions, with the order of conjunctions. Sometimes one order of conjunctions works best, sometimes the other works best. We don't want to think about the ordering of the conjunctions, and we need to get rid of that. Prolog partial deduction methods don't do that, anything about that, because they have to be considered from left to right, but we are free to not do that. And we had to make sure that we unfold the stuff that matters first. So we unfold the calls to Boolean connectives first in this particular example. And we have to make sure that we do that as much as possible to get the most information while driving. We got some results while running evaluation. We can see that disregarding of how we implemented the evaluator, our specializer got some improvement. This is the blue one here, our results, compared to the violet, which was the original one. And the green one is the Prolog partial deduction tool that we run, which worked unpredictably for these particular exams, but our method worked more or less the same for all of them. The second step that we did with Igor was to do the functional conversion. Here, the idea is that once we know the particular direction, once we've done all the specialization, we can improve it further by translating the program from miniKanren back to a function. what am I saying about this? So consider the miniKanren program addition for addition of two numbers. We can consider this implementation, and then when we know that we only run add with known first two variables, so it only works as an addition, it only computes the sum of numbers, then we can automatically translate it into a function that doesn't do any of the unifications, that only works with partial matching and stuff like that, and thus is a little bit more fast. Of course, this is all fun while we are dealing with functions, while we are dealing with relations that only produce one possible result. Sometimes it's not like that. For example, if we run our addition in the backwards direction, so we only get the result of the addition and want to get all of the summands that can sum up to it, then we have multiple possible results. For example, add or run for 1 generates us x should be 0, y should be 1, and x should be 1, y should be 0. We can somehow incorporate this idea in our functional conversion. This is where we reuse the idea of streams that represents the non-determinism in miniKanren, and thus can be representing the non-determinism in our functional conversion, in our functional program. We ran into the thing that we have to deal with monads here, but it's not very complicated. And funny enough, it generates the results that we expect in the same order, more or less, that we expect from miniKanren. And it's a nice compromise between different solutions. One thing that is not very nice is that sometimes we are left with variables that don't get any result. So for example, if you run addition with only the first argument known, when we want to find all of the numbers that are in the relation that z is x plus y, where x is known, then we get, when we analyze the first disjunction, we can only say that whatever the value of y is, the same value holds z, but we don't know what the value of y or z is. In that case, we have to still provide some results. So we have to generate possible numbers, and thus we run into this generators issue. Generators is a pain because they usually are infinite. When we have infinite numbers of results, we need to make sure that we interleave them correctly in order to at least produce some results before we run out of time. So funny enough, we can use streams for generators too. We can also represent them to be able to get all of the answers in the finite number of time. In particular, when we did that, we had to do mode analysis, which is a kind of data flow analysis that which helps us to understand what variables are known to be static and which are known to be dynamic. And using the modes, we can then understand what we can translate our unifications to. So if we know two terms to be ground, to be known, to be values, then unification between them is just the equality check. If we know only one of them, but the second one is free, in that case, it's either an assignment or a match, a pattern matching. We can also get generators, but each of them, or each of these four cases, is basically faster than the unification, the initial unification. One thing that we still have as an issue is that order in conjunctions is still crucial. So, for example, if we run the multiplication, we have two calls to relations here, to addition and multiplication. So this implementation of multiplication is just add x to the result of the multiplication of x with the number reduced by 1. And if we put the this sort of the conjunctions, we get a function that runs significantly faster and with different time complexity than if we put them in the different order. So the second case is what we call generating text. Generating text is a very inefficient strategy to do, and we want to avoid it. We do it by providing the ordering heuristic that we do while doing mode inference. We basically say that if we see something that works as a guard, then we can do it. Otherwise, we just we select in between our conjunctions stuff that restricts our search space significantly, and then push everything else for the later. Hopefully, some information about its arguments will come to fruition, and then we will be able to make them a little bit easier. And having this ordering heuristic, we get the result that we want. We got the multiplication that works faster, and of course it works for some different for other problems too. One thing that is important here is that some particular relations have an order of conjunctions that works best for one problems, but not the others. So there is no a universal best order of conjunctions that we can select. We can only do that specific for specific direction. For example, if we have a sorting relation, we can use it to generate all the permutations of the list or to sort the list. And depending on the problem, one order will be better than the other. And better means that it will be significantly better. The permutations will time out in this order very fast, while in this order the sorting will time out. And by doing our functional conversion, we can always we can get the order of the conjunctions that works best for the particular problem we have at hand. And one other thing is that I told you that we use streams for representing the sets of answers. Sometimes we don't need to use streams. By switching the monad, we can get results that also runs faster, significantly faster for some problem. And we don't really need to change the code itself. And this is one of the tricks which we employed to get it a little bit faster. So in conclusion, we created some specialization methods for miniKanren. We also created one other, or I would say two others, specialization methods for miniKanren that works better for some particular programs. We also implemented the functional conversion scheme. Combining them brings us the best results. We get some speedups. Of course, they are not as great as we would expect. You could see here probably that we can only sort lists of hundreds of numbers and not more. And it's of course not very nice. But at least we got some improvement to the miniKanren search. Okay, that's all from me. If you have any questions, I am ready to answer them.
Good question. You started your talk with referencing that Prolog was developed as like you can feel it as LLMs 50 years ago, but today you have big language models, and like why can't we use them for like doing the same thing that's like the miniKanren tries to do?
This is a great question, I would say. One thing that LLM does not understand is logic. One thing that Prologs understand is logic. So if you want to get a solution that is correct all of the time, you need to use something that is more specific and more smarter than LLMs. You cannot explain the logic to them, unfortunately.
But actually, it is kind of a question because there's some possible ways to help language model to check. For example, there's some languages as POCs that
Yeah, I understand. Of course, you can kick LLM until it spits out some program. You can check if that program is correct. It can be incorrect, then you throw it out. You kick LLM until it spits out that problem, and you continue this process until you get something feasible. But LLMs, they hallucinate, they generate stuff that doesn't make sense. You sometimes struggle to make them listen and understand what you are trying to say. There is not such a problem in prologues and other logical programming languages, because the logic is the whole language, basically. If you can speak in first order logic, the language will understand you. This is 100% correct, but slow. LLM is hopefully faster, but like 5% correct or something. And you need to make sure that the solutions that it spits out is correct.
But like my question is, I think, more about the future, because you did a great work to increase the performance, so to be able to source 100 numbers faster. It's cool, but like at the same point, language models, they improve each year significantly and can solve now much more complex tasks. And like, do you see that in some future, miniKanren can do something like really special that's even like that you can't achieve with LM, like with making many requests and checking them?
I would say that the tools are good in different spheres. LM is good to understand what you're saying in natural language. Sometimes it can translate it into logic. Then you can shove it into a logical programming language and get the results you want. The thing is that some applications just cannot handle any kind of mistakes. If you are dealing with medicine, you don't want a hallucinated LLM to contribute into your diagnosis. I think, actually, it's my belief. But of course, if we are talking about some less like crucial parts, like, I don't know, to design a website, you probably would use LLM, right? Not Prolog. But if you need to make deductions, then Prolog's use better. Okay.
So I have one question. So you said that for like critical applications, you use Prolog for like relational programming, but I guess like a lot of things developed in this area, they don't have any formal proofs about them being correct, right?
I would say that they're correct by construction, unless you can break the first order logic that is underneath the hood.
Yeah, but I mean, like, so you developed some like specialization technique. How could we? Why should we believe that it's not changing semantics?
Okay. So basically, what we do with our specialization is reordering conjuncts that doesn't affect the answers in miniKanren because of the complete search. It only like puts them in different order. And the other thing is we substitute constants. This also cannot break anything. We don't add anything to our program. We don't delete anything from our program while doing specialization.
But still, like you, yes, since you affect termination of some queries, you kind of changing the semantics.
The termination is a thing that is, I would say, beneath the point, because in Prolog, it is true that some queries cannot terminate, and if you reorder some conjunctions, it will start terminate or it will stop. In miniKanren, it's not the case. The only non-termination that can happen in miniKanren is after it already computed all of the answers you have. So this is the complete search. It will either generate all of the answers and stop, or loop forever, but only after it generated everything.
Are there any certified implementations of miniKanren?
I don't think that there is a certificate. No, sorry, there is. There is. Yes, of course. We have developed several years ago. Rasplofas Dmitry created it.
What
So
are the
this is-
limitations of the certified version? Could you extend it with like your approach?
I mean, I could, but why?
I mean, like if you want to use miniKanren in like critical applications, maybe you want to have it and improve that code is correct.
Yeah, I mean, there is some place when we need to stop not trusting our tools. And I believe that miniKanren is small enough to be able to prove that it works by staring at it. Basically. I showed you the whole implementation, more or less. This is the whole implementation of miniKanren.
But I guess like many years of your work on miniKanren produced a bit more code. than just
I mean, this is the
lines.
miniKanren, there is no specialization here.
Yeah. That's what I'm saying. So like
Maybe my specializer
harder
has
to-
bugs. Yes, my specializer may have bugs. This is completely true.
Okay.
Do you want me to create a specialized version of my specializer? Sorry. I mean, I can do certified specialization, but it will take me another 7 years, maybe. Do we need to do that?
Let's do that.
Oh, okay. God damn it.